Welcome to the presentation on design of a single-stage bidirectional onboard EV charger with reactive power flow capability and vehicle-to-vehicle battery charging operation. I, Sayyid Arfat Alam Qadri, along with my colleagues Preksha, Rishik, Vasili Siddiqui, will be presenting today. We are Group B9 and our supervisor for this project is Dr. Ashraf Ali Khan. In this presentation, we will be talking about conventional two-stage EV charger, single-stage EV charger, heat sink design, conclusion and further work. In the first semester of this 2-semester long project, we have performed literature review to understand the current trends in the EV industry. We have modeled and simulated a conventional two-stage bidirectional charger and also a novel single-stage bidirectional charger and the heat sink for EV applications. Conventional two-stage onboard EV charger. In conventional topology, there are two converters involved. Three-phase power is first supplied from the grid, which is converted to DC by the first stage converter to charge the vehicle battery. While in the second stage, power is converted to AC to feed the induction motor. In the bidirectional flow, EV charger is capable of accepting the energy from grid as well as delivering it back to the grid. In the G2V, that is grid to vehicle operation, battery is charged, while in the V2G, battery discharges to supply power back to the grid. Although unidirectional chargers are popular because of their simplicity and low battery degradation, the recent advancements have shown the possible capabilities of electric vehicles as mobile energy sources, which can be used to supply power back to grid during peak demand hours, also when other renewables like solar are down during evening hours. Furthermore, bidirectional onboard chargers can also be used to charge other vehicle batteries in V2V application. This slide shows the Simulink model created for a bidirectional charger. A three-phase grid power supply is modeled with 240 volt line-to-line voltage. Filters are connected to the incoming power supply to remove any harmonics. The first stage power conversion happens in AC to DC converter, that is rectifier. The DC output of the same is regulated using one buck boost converter. Lithium ion battery of 154 kilowatt hour capacity is modeled as in Tesla Model 3 with the nominal voltage of 350 volt. The battery output power is then converted to AC using an inverter to feed the induction motor of 150 kilowatt capacity. Again, the motor rating is selected as per Tesla Model 3 specifications. Both the power converters, AC to DC and DC to AC, are IGBT based with 6 switches individually. The control circuit consists of PWM generator for AC to DC and DC to AC converters and the gate pulse generator for buck boost converters. In the G2V mode simulation, the gate pulse generator circuit is given minus 30 input to simulate power delivery to the grid, whereas for vehicle to grid simulation a plus 30 constant input is given to simulate the power delivery from the battery to the grid. The simulation plots for voltage and current delivered to the grid from vehicle are shown on this slide. As can be observed, the desired sine wave voltages and currents are present. The individual phase voltage is little less than 200 volt peak. Hence, we can calculate that the phase to phase voltage achieved is 240 volt RMS as per grid specification, while current value is around 29 amps RMS. As seen on the graph, the DC bus voltage is stabilized at 800 volt in 0.4 seconds. The state of charge drops from initial value of 50% to approximately 49.99% during the simulation time of 1 second. The current delivered by the battery goes through initial transient fluctuations and stabilizes at around 30 amp value. Now the second case of grid to vehicle mode, that is when grid supplies the power to the vehicle. The plots shown on the slide are of three-phase voltage and currents. The voltage value can be seen to be fixed and sinusoidal at the specified grid voltage of 240 volt phase to phase, whereas the current delivered to the vehicle is approximately 30 amps RMS. During G2V mode, battery voltage rises from 378 volt to 380 volt in 0.8 second. The state of charge increases from 50% initial value to 50.0035% final value within 1 second simulation time. Since current is being delivered from a grid to vehicle, the plot shows negative 30 amps RMS value.
The next topic is single-stage bidirectional EV charger. Unlike conventional ones, this type of chargers have only one converter in order to convert AC power to DC power and vice versa. The advantages of single-stage EV chargers are compactness of charger, economical operation, and reduced losses, which eventually results in higher efficiency. In single-stage topology, the converter takes power from grid to charge the battery and supplies back the power from battery to grid. An induction motor is connected between grid supply and the converter, and the flow of electric power between grid, induction motor, and converter is controlled using the changeover switches. To design the single-stage EV charger, we have used the MATLAB Simulink, and this is the actual model of the charger. The circuit includes a three-phase grid supply connected to a bidirectional converter and a 150 kilowatt induction motor. The ratings of an induction motor is based on Tesla Model 3 specifications. A set of two circuit breakers CB1 and CB2 is used as a changeover switch to control the flow of electric power between grid, induction motor, and the converter. Also, to correct the power factor, combination of inductors and capacitors are used. As a part of single-stage topology, only single bridge, which consists of full bridge front-end converter and buck-boost converter, is used as a rectifier and an inverter both. The control circuit for this model is similar to that of the conventional charger model explained earlier. Also, this model runs for both grid-to-vehicle and vehicle-to-grid mode. For G2V mode, circuit breaker 1 is made closed and circuit breaker 2 is made open, and a constant of -30 is given to the control circuit. In this manner, the battery gets charged by grid via converter. Similarly, for the vehicle-to-grid mode, again CB1 is made closed and CB2 is made open, but this time a constant of +30 is given to the control circuit. By this arrangement, the grid takes power from battery via converter and the battery will gradually be discharged. The slide shows the simulation results for single-stage charger. The two graphs exhibits the performance of battery during two modes. The top left graph shows the state of charge of battery during grid to vehicle mode, where it charges from 50% to 50.005%. Similarly, the graph on the right bottom shows the discharging of battery during vehicle to grid mode, where it discharges from 50% to 49.995%. All other graphs such as current plots and voltage plots for both battery and grid, are similar to that of the conventional charger plots. The next is acceleration mode. In this mode, electric vehicle is in running state, with motor being fed from the battery. To achieve that, the grid is isolated from rest of the circuit by making CB2 closed and CB1 open. The induction motor gets power from battery via converter and starts to rotate. The rated speed of induction motor used here is 1785 rpm. So, we have maintained equivalent speed of 183 radians per second in the circuit.
Hi, my name is Rishik Karir and I am pursuing Masters of Applied Sciences in Energy Systems Engineering. We have designed two models of heat sinks. All the made engineering drawings and simulations are done using SolidWorks software. Starting with introduction. So heatsink is the necessity of any electronic equipment which is required to remove extra heat from component to increase the reliability of equipment. So displayed are some steps for removal of heat. First step is the source generates heat. This source may be any system that creates heat and require the removal of said heat. Second step is heat transfers away from the source. In direct heat sink contact application, heat moves into the heat sink and away from the source via natural conduction. We have used aluminium alloy 6061 to construct the heat sinks. Third step is heat distributes throughout the heat sink. Heat will naturally travel through the heat sinks via natural conduction, moving across the thermal gradient from a high temperature to low temperature environment. Next step is heat moves away from the heat sink. This process relies on the heat sink's temperature gradient and its working fluid, which is air in our case. The working fluid passes across the surface of the warm heat sink and utilizes thermal diffusion and convection to remove heat away from the surface into the ambient temp environment. This slide speaks about considered conduction and switching losses. We have used datasheets of components downloaded from DigiKey. So calculated load for conduction and switching are 642.2 and 32.8 watt respectively. Total loss is 675 watts. This slide represents considerations which we have taken into account while creating heatsinks model. We have created model with rectangular vertical fins which is considered to have uniform cross-sectional area. Material is assumed to have constant properties. There is negligible radiation exchange with surroundings. Also listed are some values like thermal conductivity of aluminium alloy 6061, density of air is taken as 1.02 kg per metric cube, ambient temperature is 298 Kelvin, dynamic viscosity of air taken for calculation is 1.983 into 10 raised to power minus 5 Newton second per meter square. In natural convection, the velocity of moving air is unknown. Thus, we cannot use the Reynolds number in the computation. Instead, we have used Gasoff number to correlate natural convection flows. Listed are some formulas which we have used for both of our designs to know about spacing between two fins, fin thickness, convection heat transfers, etc.
In this slide, we are going to see how we have designed a single heat sink for the complete charger. In order to design a heat sink, we would need few parameters such as fin spacing, fin thickness, convective heat transfer coefficient, and height of the fin. We have calculated fin spacing by using Reynolds number, Prandtl number, and Grashof number, and we have got the required fin thickness as 1.053 mm. And with the use of Nusselt's number, we have calculated the value of convective heat transfer coefficient, that is, which is denoted by H, and by trial and error method, we have found out the value of required height of the fin which is 115 mm. In order to compare a larger single heatsink with that of the smaller heatsink, which would cover only a smaller area or part of a charger, we have designed a heatsink for two switches. This heatsink will cover only power losses generated by two switches of the MOSFET or inverter. Here we have calculated optimum fin spacing, fin thickness and convective heat transfer coefficient as done for the first heatsink. Also we have calculated height by trial and error method, which comes out to be 115 mm. The only difference in designing is the length and material required between heatsink 1 and heatsink 2. In the larger heatsink, as it was a single heatsink for complete charger, its length was large, that is 110 mm, while the length in second heatsink is only 40 mm. After calculating the inputs required to design a heatsink, we have modeled a heatsink in the SolidWorks software, and further we have done a thermal analysis of it. Now on the left hand side of the slide is the thermal analysis result for the single large heatsink, and on the right side we can see the thermal analysis result for the smaller heatsink. The larger heatsink was able to lower the temperature from about 1500 Kelvin to 400 Kelvin, whereas the small heatsink is capable of bringing down the temperature from about 715 to 323 Kelvin. To conclude, with our research study, we have come to a point that a single stage charger is more efficient, economical and emits less heat as compared to that of the conventional charger. This is because a single stage charger requires less number of components as compared to conventional charger. And on the heatsink side, we have come to a conclusion that a single large heatsink is more economical than multiple smaller heatsinks. This is because a single large heatsink requires less material as compared to that of the multiple smaller heatsink. So if you want to design a heatsink for any charger, we should select a large single heatsink instead of smaller multiple heatsinks. In the second part of our project, we are going to design a PCB hardware for the electronic vehicle charger. Also, we are going to design, simulate and do analysis for vehicle-to-vehicle charging, along with designing simulation and analysis for reactive power flow capability for grid stability purpose. And for the heatsink, we are going to design and do simulations on Cosmol multiphysics software. Thank you.